In this first example using Monte Carlo integration, we're once again going to revisit that first problem that we looked at with quadrature. So I just copied and pasted from that first example so we can get kind of a baseline here. So we say that using quadrature on this function, again, we got this value of 6.7975. So we want to see, using Monte Carlo integration, not quadrature, are we going to get the same value, and how many samples do we need to take in order to get that value? So the first thing I need is to probe my function, or keep taking different values of my function so that I can assemble an average value that I'm then going to use to find the integral. So I'm going to use these test points, I'll call xt, and I want to sample them on a uniformly distributed range from 0 to 5. So I want to use rand. I'll just start with 1,000 points. So 5 times, or 0, I can do plus 5 times rand. So what this gives me are random numbers between 0 and 5 with a uniform distribution. And I only want one column of them. So if I look at the values of xt, random numbers again between 0 and 5, because those are the bounds of integration. So I want random numbers between those 2 points, uniformly distributed. Big F are going to be values of my function evaluated at those values of x. So my function is fun1. I want to keep evaluating it at all those values of x. Right, so those are all the function evaluations at those values of xt. Right, so that's the total. So what I want, or those are all those different evaluations I made. What I want to find are the average value of all of them. And then this is my estimate to the average function value. So my estimate to the average function value, 1.3852. So if I want the integral, going back to the definition of this, I want to multiply that average value by, in this case, the length, which is the upper bound minus the bottom bound, is going to be 5. So this is going to be my estimate as to what the value of the integral is. So using 100 points here, my estimate is 6.9262. Rerunning this, what I'm going to take as the true value, 6.7975. So they are a little bit different here. And every time I run it, I'm going to get a slightly different value for what the estimate of what my integral is using the Monte Carlo integration method. But as we saw before when we use Monte Carlo simulation, in general, the more points I use, the better my estimate is going to be. So let me rerun this and use 1 times 10 to the 5th points instead. Right, so we see here the actual, or the accepted, 6.7975. With 1 times 10 to the 5th, I get 6.8074, so pretty close. And let me use, just for this example, 1,000,000 points. And we see that we're getting closer and closer to the value. In this case, I know what the integral should be, or the accepted value, so I know when I'm getting close to it. But in general, that might not be the case if I can't find an analytic, or if I don't know the analytic solution, or I can't use quadrature to get there. So to show that it's a good estimate, or to kind of prove to ourselves it's a good estimate, we want to again try showing convergence of our sample. So basically, we want to see how many samples does it take before the estimate of our integral converges, or doesn't really change much as we keep adding more and more values. So what we can is, instead of just using the million at the end, I want to see, by taking the average of the first value, the first 2 values, the first 3 values, etc., I want to see how does the estimate of my integral change as I add more and more samples. So I could use a for loop like I did before when we were first talking about Monte Carlo simulation, but we saw that that was a pretty slow method to do it. A different way I can do it is, instead of using a for loop, I can use the cumulative sum of f. So what does the cumulative sum do? Well, it's printing out a bunch of values here I don't really want to see, but I'll call this fs for right now. So what cumulative sum is the first entry in it is the first value in f. The second value in it is the sum of the first 2 values. The third value is the sum of the first three values, etc. So it's accumulating the sum as I go in the values of f. So we see that it just keeps getting larger and larger as I keep adding the first n values of f. Right, so instead of using that function mean, I can now take the mean by dividing by 1 to the length of fs. So what this is going to do is it's going to, since I'm using a dot division here, the first value in fs, it divides by 1. Then the second value in fs, it divides by 2. And then the third value by 3, etc. So effectively what this is doing is it's going to be finding the average value. Because if you think about what fs is, it's the sum of the first value, then the sum of the first 2, then the sum of the first 3. So I'm taking the arithmetic average kind of automatically this way. And that's going to be my estimate of the integral. Okay, it didn't like that this first time because they are not the same size. I have to use the transpose here. Right, so now with the transpose, I do have IE, and we see it has 1,000,000 points to it. So first, let me just look at the last point of IE. Oh, and one thing I forgot to multiply it by that 5, which was the length between the end point and the start point. So again, with 1,000,000 points, we see that it's pretty close to that value we get from the quadrature. But now let me do a semi-log plot so I can look at the convergence of it and see has it converged and when that did happen. So I want to look at the value of my integral. And I'll have the grid. Right, so we see my y-axis is the value of the integral, x-axis is the number of samples I'm using in the Monte Carlo integration. So we see we're way overestimating at first, and then we start to kind of close in here, we start underestimating, and then we come back in to the value that we like. So it flattens out around, really well around here. So if we just put a little blip down there, we see that around, I'll say 4 times 10 to the 4th, it's converged to the value, pretty close to what we said was the accepted value for this. So since we showed that it's converged at around 4 times 10 to the 4th, we know that up here, let me find, coming up here, this is my final estimate, is just going to be 5 times the mean of f. Right, so again, that was the final estimate I have of my integral, 5 times the mean of f. So we know that it's more than, it's converged by the time I take 1,000,000 samples. So one more thing I want to do is compare how long it takes for MATLAB to run these two routines. So I'm going to put a tick and a talk up here, how long it takes to use the quadrature method. And then I'll put a tick up here. So these are steps only for finding the Monte Carlo integration method. So I will include the making of this x vector, I will include making of the f vector, and then taking this mean over here, just for comparison purposes. And I'll just run this section. All right, so we see here, using the quadrature, it took about 0.093 seconds, and this was the result, 6.7975. In the second part down here, I got a very close value, 6.7971, using 1,000,000 samples, and we see that it took MATLAB 0.07 seconds to run that part of the routine, the Monte Carlo part of that routine. Let me suppress the printing so we get a little bit better of an estimate here. So again, we see it took a shorter amount of time in this case to run a 1,000,000 sample Monte Carlo method than using the numeric quadrature. And on my computer, let's see, it took about 25% longer to run the quadrature than it did to run the Monte Carlo integration. Now I can run this a couple times. I'll call this T1, call this T2. So running again, about 12% longer, 45% longer, about 66% longer every time I run this. So I'm seeing that it's always taking longer to run the numerical quadrature than it is to run the Monte Carlo integration in this example. So to recap on this one, we did, using numerical quadrature, know what the answer, or at least the accepted answer, was going to be. So we recreated that answer using Monte Carlo integration. I'll run this whole thing one more time. And we see that using 1,000,000 samples was enough because we've converged before then at about 3 or 4 times 10 to the 4th for the value of what that integral was for estimating what the value of the integral is.